Bismillah ar-Rahman ar-Rahim, alhamdulillah, wa salatu wa salam ala Rasulullah. I would like to thank everyone for coming tonight. Tonight we have a special guest, Dr. Sultan Alamer. I would like to welcome and congratulate him in completing his PhD in 2021. Dr. Alamer finished his master back in 2014. Dr. Alamer received both master's and PhD degrees from the University of Connecticut. Dr. Alamer research interests includes DNA analysis, single cell analysis, cloud computing, signal processing, machine learning, and brain-computer interface. Dr. Alamer has published many journals and reviewed a couple of articles in high-impact factor journals. Tonight, Dr. Alamer will present his PhD work titled Lossless Compression Tools for Genomics. Let's begin our presentation tonight by welcoming again our guest, Dr. Alamer. We will have some time for questions after the talk, inshallah. Thank you so much. You can start now, Dr. Sultan.
Okay, thank you so much, Dr. Yusuf, for the introduction. And good evening, everyone. And thanks for coming. My name is Sultan Alamer, and today I will be describing my work on lossless compression tools for genomic data. So let's start by giving you the outline of today's presentation. At first, I'll be talking about the background and motivation for this research. Then I'll briefly be talking about data compression in general. Next, I'll be explaining the first tool we developed, which is based on unbalanced Huffman Tree implementation, how it works and how it performs against the standard Huffman Tree and other tools that are based on Huffman Tree in terms of compression ratio. After that, I'll be describing the second tool, which is based on an ungreedy Huffman Tree implementation, how it works and how it performs against the unbalanced Huffman Tree implementation and the conventional Huffman Tree implementation. Then I will be talking about another tool that is based on multiple non-greedy Huffman Tree implementation. We will see how it works and how it performs against the single non-greedy Huffman Tree. Finally, I'll be talking about the last tool, which is a tool that is developed for a different file format, the Elfastekuc file format. I will explain how the tool works, how it compares to the state-of-the-art tools, and the result of this comparison. So let's start with the background and the motivation of my research. When talking about the genomic data, we should start with the basics, which is the DNA. So let's learn more about DNA and its nature and properties. So the DNA carries the information blueprint and the mechanism that translate the DNA code into instruction for how organisms live and develop. The DNA consists of a chemical building block called nucleotide. The order or sequence of these nucleotides form the instruction in the genome. There are 4 types of nucleotide bases: adenine, cytosine, guanine, and thymine. The DNA has various forms of repetition: direct and tandem repeats, reverse, complemented, and palindrome and approximate repeat. The DNA also has 2 parts, intron and exons. The intron is non-coding area, generally more redundant, and it makes up of 50% of the genome. And the exon, which is coding area and generally less repetitive. To better understand DNA, it has to be sequenced. So what does DNA sequencing mean? The DNA sequencing is the process to determine the order of the 4 bases, A, C, G, and T in the genome. So why DNA sequencing? The DNA sequencing provides information about the coding and non-coding parts of the genome. It's also helpful to fetch out important pathways. It's also used for evolutionary studies and species comparison. The DNA is beneficial for more effective personalized medicine. For example, why drugs work for person X and not for person Y. It also can help in many other gene-related diseases. The researchers have already sequenced multiple genomes, including the human genome. The genome of different species are vary in size, chromosome, and gene numbers. The genome is saved in computer as text-based file. The human genome requires more than 3 GB of computer storage. In the beginning of DNA sequencing technology, the sequencing was expensive, slow, and had low throughput. An example of such technology include Maxim Gilbert sequencing and Sanger sequencing. When the human genome started back in 1990, it was planned to finish by 2005. That means 15 years for a single genome. It also was estimated that the project would cost a total of $3 billion over that period. However, with the help of advancement in sequencing technology, the project ended 2 years earlier and cost less than $3 billion. The technology kept advancing, and it was led by what was called next generation DNA sequencing technology. The next generation DNA sequencing are better than earlier technology because they are massively parallel, have a high throughput, are able to randomly sampling for a fragment, and multiple fragments are sequenced at once. And they came at lower cost. Some examples for next generation DNA sequencing are massively parallel signature sequencing, Bolognese sequencing, the 454 bio sequencing, Illumina sequencing, and solid sequencing. The major advantage of the next generation sequencing over the older technology is cost. With the help of innovations in chemistry, optics, fluidic computational hardware, and bioinformatics solution, the cost of DNA sequencing dropped significantly. The Human Genome Project would only cost around $5,000 back in 2015 instead of $2.7 billion. Another sequencing technology generation has emerged and led to another drastic drop in the cost of sequencing. Not only this, but it also provided other advantages like longer reads, portability, and speed. This has boosted and will boost the sequencing research by a lot. Using this technology, the Human Genome Project will get the human genome will get sequenced for less than $1,000 as of 2017. Nanopore DNA sequencing and PacBio are examples of the third generation sequencing technology. Although the next generation sequencing technology and the third generation sequencing technology provide lower cost and high throughput, speed, and portability, they also introduce what is called data deluge that data centers are facing nowadays, including the gene bank. We can see in the chart that the gene bank size has increased exponentially, and that because of some important genomes are in the order of billions of base pair, exponential growth in the number of completed genome, exponential growth in the size of available DNA sequencing, since we have a higher coverage. So we need an efficient and effective way to reduce the DNA file fingerprint, and this can be done using tools for sequence compression. In this section, we will learn more about data compression in general. In computer science, data compression in a nutshell is the process of encoding information using fewer bits than the original representation, while maintaining the original form. Compression is very useful to save on consumption of expensive resources, such as storage and bandwidth, as well as saving time of downloading the desired file. The compressed data often need to be decompressed to be readable by human or computers. There are trade-offs for compression like, how well we can compress a file, what is the amount of distortion introduced if allowed, and what are the computational resources required for the process. There are two types of data compression. The first one is lossless compression, and the second one is lossy. The lossless compression makes use of the data redundancy, and it's used when a file needs to be recovered exactly, such as text in documents, computer program, etc. Run-length encoding, Limble, Ziff, Wallis, and Huffman Tree encoding are famous lossless compression technique. On the other hand, the lossy compression take advantage of the data redundancy and irrelevant data, such as data that human cannot see or hear in video, image, or audio files. In the next slides, I will be talking about the first tool, which is based on unbalanced Huffman Tree implementation. First, we will learn how the algorithm behind this tool works. The unbalanced Huffman Tree section is part of our published work in the Journal of Computational Biology in 2017. The algorithm for this tool in general works as follows. First, we perform a run length encoding on the genome in order to encode any repetition of the same base. For example, the RLE for 7As, let's see, is A7, and we will have R as a set to collect these tuples. Then scan the whole genome and collect the frequency of each substring less or equal K. Then let A to be the set for those collected k-mers. Then find the set S that which by encoding we got the best compression gain. More about this later. After that, and since the genome may have non-ACGT bases, those bases need to be collected in a set M. This step can be merged with step number 2. Then after that, we input the collected sets, the S, R, and N to the Huffman algorithm to get the bit code for each member of each set. Then start the encoding process by scanning the genome and replace each base, k-mers, or tuples by its bit code. Finally, we convert the bit code into ASCII and add the headers as well as bit code for each symbol. To force the conventional Huffman tree to be unbalanced, we follow these steps. First, we sort all collected k-mers where k is smaller or equal to based on their frequency. Then we select the k-mer with the maximum frequency, let's say f. Then we scan the k-mers with frequency less than f in descending order until a k-mer with a frequency less than half of f is found. After that, we select this k-mer and store the frequency of the selected k-mer in f. Then we repeat steps 2 and 3 until no more k-mer can be selected. Finally, we input to the Huffman encoding algorithm the k-mer that are selected above, along with the 4 bases and their frequency. Our experiment setup was as follows. We choose DNA datasets of 5 different species, including the chromosome 22 of the human. The size of these datasets vary from 4 megabyte up to 50 megabyte. In our experiment, we use a machine running 64-bit Ubuntu and 2.8 gigahertz Intel Core 2 quad processor and memory space of 8 gigabytes. We compare against the standard Huffman tree, gzip, which uses LZ77 plus Huffman tree, and bzip, which is used for Wheeler transformation plus Huffman tree. This tool is developed to compress FASTA and multi-FASTA files. The FASTA is text-based file. The sequence in FASTA format begin with a single line description called the header, then followed by lines of biological sequence. The header always starts with the greater than symbol in the first column. In the next slide, we will see the result of this section. First, we compare against the standard Huffman tree. For all data in the dataset, our tool shows significant improvement over the standard Huffman tree. We tested different K, which is the number of k-mer to be encoded for both standard Huffman tree and unbalanced Huffman tree. For all genomes, unbalanced Huffman tree provide better compression ratio that reach 3%. Chromosome 22 was a special case since it has a lot of N bases, so we don't see any significant improvement. We also compare against gzip and bzip2, since both of them uses Huffman tree and are still widely used to compress genomic data. Our tool also deliver better compression ratio that reached to 6% against gzip and 3% when compared against bzip2. Chromosome 22 is the only genome that our tool was not able to deliver the best compression gain, and that because of how our tool is dealing with the N bases, which will be addressed in the next tool. Our next tool is another Huffman tree based that is built on non-greedy Huffman tree implementation. The non-greedy Huffman tree section is part of our published work in the Journal of Computational Biology in 2019. Before developing this tool, we take into consideration 3 things that we faced while working on the unbalanced Huffman tree. Huffman encoding is greedy algorithm, but we can build the optimal Huffman. run length encoding does not contribute much in the compression gain in general. And not all k-mer created equally. We mean their impact on compression gain in general. The algorithm works as follows. First, the frequency of each base ACGT is calculated. At the same time, the non-ACGT bases and the starting position of the M bases and their ending position are marked. The base that appears least frequently is determined using step 1. The frequency of each k-mer, in this case, k equal to, is collected. Find the optimal two-mer, which by encoding, the base 4 count is minimized and the two-mer count is maximized. After that, a Huffman tree based on the above is built. The 4 bases and 1 k-mer are encoded with their Huffman encode generated from the previous step. And finally, the encoded sequence is converted into ASCII code with the addition of headers. The experimental setup is the same as the previous tool, so we'll skip it. The result. These two tables are a real example of encoding information for the same genome for non-greedy Huffman on the left and greedy Huffman on the right. To provide better compression or to restrict encoding to a single k-mer, which is 2-mer. So the table on the left has 4 bases and 1 2-mer to encode, while the table on the right has 4 bases and 5 k-mers, which are 2 3-mers, 1 4-mers, 1 6-mer, and 1 8-mers. There are multiple k-mers with a compression impact ratio that reach to 12% in the greedy example. However, their frequency are not high enough to balance the impact that the base 4 put on the compression gain. Whenever adding a k-mer to the table, we need to increase the code length by 1, and this is to maintain the prefix property of Huffman tree. The 2-mer frequency is always high enough to reduce the overhead of base 4 and improve the compression gain in general. Since our tool includes one of the 4 base and the 2-mer with 3 bits, these two determine the compression ratio gain since the other 3 bases encode for 2 bits and have the same impact on the compression ratio. This table shows that the non-greedy implementation of Huffman tree always result in fewer total bits for the base 4 and the 2-mer, which lead to create smaller file. As you can see in the greedy size on this table, the 2-mer for the cholera is double T and the base 4 is C. In the encoding process, our tool starts with encoding the 2-mer first, in this case, the double T. And this will change the base frequency since a lot of T bases will be taken out of that file. The greedy Huffman keeps the base 4 as the least frequency base without seeing the whole image, while on the right side, the non-greedy algorithm adapts to the change and pick the new lowest frequency base, which is in this case T. No wonder, because we already encoded a lot of the 2-mer, and this has decreases the frequency count for the base T. In the second genome, the algorithm even changed the 2-mer from CG to TC, since the 2-mer TC and the base 4T will lead to maximize the 2-mer and minimize the base 4 when compared to all other possible options. The other genome followed the same behavior for cholera, and the algorithm ended updating the base 4 only. In all cases, the total bits decreased by a lot when using non-greedy approach. We compared the non-greedy implementation against the previous greedy and balanced Huffman tree implementation and both gzip and bzip2. The compression ratio defined as the ratio of the compressed file size to the original file size. For all genome, the non-greedy implementation show improvement in the compression ratio gain compared to the others. The improvement reached 1 to 2% when compared with the unbalanced Huffman tree, and reached 5 to 7% when compared with gzip, and reach 3 to 4% when compared against ReZip2. Since there are only two specialized compressors in this comparison, the non-greedy Huffman Tree and the unbalanced Huffman Tree, and both were developed using the same language, Python, we compared their speed against each other. So when comparing the compression time to our previous tools, the unbalanced Huffman Tree encoding tree, the non-greedy implementation performance reaches to 7 times faster than the unbalanced Huffman Tree implementation. The same for the compression speed. As you can see in the chart, the non-greedy is way faster than unbalanced Huffman Tree. And the unbalanced Huffman Tree is significantly slower because it has more k-mer to encode, so it needs to scan the genome multiple times, in addition to the RLE that puts some overhead without being very beneficial to the overall compression gain. The next few slides will be about another Huffman Tree-based tool, which is based on multiple non-greedy Huffman Tree. And the multiple non-greedy Huffman Tree section is part of our submitted work to the PLOS ONE journal in 2020. While working on the previous tools, we noticed that the basis frequency vary across the genome. That means we will have more than a single optimal Huffman Tree. This tool is based on non-greedy Huffman Tree, but instead of using single tree, the tool uses multiple non-greedy Huffman Tree. Each tree used to compress different parts of the genome. The algorithm works as follows. First, we split the desired file into n partitions. For each partition, the frequency of each base is calculated along with marking in bases and the non-ACGT base. Find the least frequent base in each partition. Then find the frequency for all tumor for each partition, and find the optimal tumor that lead to minimize the base for and maximize the tumor count for each partition. After that, we built the Huffman Tree based on the previous step for each partition. We encode the tumor and the 4 bases using their bit code generated by Huffman Tree for each partition. Then we convert the bit codes to ASCII plus the header that contain the Huffman Tree information. The dataset used to test our tool contains 5 FASTA files and 3 FASTQ files. In the FASTQ files, we only compress the sequence stream. Since there is a big difference between FASTA and FASTQ file in terms of size, we split the data into 2 groups, FASTA file group and FASTQ file group. FASTA files are only partitioned up to 128 partition, and in this table shows the size of each file after the partitioning. P1 means no partitioning, and in this case means we are using the single non-greedy Huffman Tree, while P4 means we split the file into 4 partitions, and each one is in size of 1 megabyte in the case for the cholera. On the other hand, we partition the FASTQ file up to 8,000 since they are very large. As before, P1 means no partitioning, and P8 means we have split the first file in the first column into 8 files. Each one of them is in size of 70 megabytes. Next is the result of our experiment. First, for the FASTA files, the cholera and Elfastekuc files have the best compression ratio gain at P equal to. Then this gets worse around P equal 32. For the SC file, the improvement is not noticeable and it gets worse at P equal 16. For the NC file, the best compression ratio gain was when P equal 8. And for the chromosome 22, the best compression ratio was when the P was equal to 17. Both compression ratio gain get worse around P equal 32. For FASTQ file, The first file compression ratio again kept improving until B was around 500. Then after that, it kept degrading. Then it reached the compression ratio of the single 9-degree Huffman Tree at around 4,000 partition. The second file compression ratio again kept improving until B was around 2,000. Then it degrades and we reach more than 8,000 partition, and it still have a better compression ratio than the single tree. The last file compression ratio gain also kept improving until around 2,000. Then it degrades and we reach more than 8,000 partition, and it still have better compression ratio than the single Huffman Tree. The results suggest that the best partition size is in range of 1 megabyte to 3 megabytes, mostly around 1 megabyte. The larger files get more compression ratio gain. We can improve the performance by decreasing the metadata footprint. And unlike other technique, the compression ratio improves with the increment in P up to a certain point. This tool is perfect for using multiprocessing since each partition is processed independently. Next tool is Elfastekuc, which is a lossless reference-free Fastekuc compressor. The following slides are part of our published work in PLOS ONE journal in 2019. This tool is designed to compress Fastekuc file. The Fastekuc file has a format that differs from Fastekuc file. They are the same since both are text-based file, but along with the biological sequence, the Fastekuc file has another 3 streams, which are the identifier, the identifier plus an optional plus sign, and the quality plus.
If you could just give me the host, please, Dr. Sultan, so I can mute.
بس لحظة. ما حصلت المايك هذا بس.
تتجه إلى اسمي وتسوي ميك هوست. أو تعمل ميوت للأخت حلا مباشرة. ممتاز.
الاسم اوكي. اسم بالعربي او الانجليزي؟
يوسف. اسمي تروح على اسمي
اوكي حصلت. شكرا دكتور. And the 4 streams come in this order. The first line is the identifier, which contain information about the sequence and the machine used to generate it. The second line is the sequence itself. And the third line is plus sign, and it's optional to have the first line next to it. And the last line is the quality score corresponding to the sequence. So when compressing Fastekuc file, we need to take in consideration the following. Is it going to be lossy or lossless compression for the quality score and the identifier streams? The sequence has to be lossless. Is it going to be reference-based or reference-free? What metrics are we working on to improve, like the time or compression ratio? How will this tool is going to compare against the general purpose compressor, because they are still in use, and how to approach the differences in the structure of the 4 streams in Fastekuc files, and what technology to support, since they have different properties like read length and different encoding. Next is how this tool works, and we will start with the experiment setup. In our experiment, we make sure to use a public data that are accessible for everyone. We also make sure to use a data that have been used previously by others. We also make sure to include different sequencing technologies such as solid, Solexa, Illumina, PacBio, and Minion. And the data sets we have are vary in sizes and coverage depth and from different species. We use a machine running Ubuntu 64 bits that is running on i7 and uses 8 GB of RAM. We compare against the state-of-the-art tools in addition to gzip and bzip2. Our datasets contain 15 files from different species and from different technology. The coverage depth is in range of 0.07x to 367x. Have a different read length. Some files have very read length within the file itself. We also have other that have short reads like 25 bases and long reads like around 6,000 and more. Finally, the datasets are in range of around 200 megabyte up to almost 5 gigabyte. We use the latest and the state-of-the-art tools to compare against plus gzip and bzip2. For each tool used in our comparison, we use the parameter suggested by its creator. This parameter combination delivers the best compression ratio. Some tools have different sets of parameters that are designed to work the best on different sequencing technology. The approach behind our tool is split the Elfastekuc file to different streams, find the best algorithm to compress each stream. And our finding was as follows. First, the probabilistic model is the best overall model to compress sequence stream. Second, context mixing algorithm are the best to compress quality score. And lastly, we split read identifier one level, then use context mixing algorithm, and that shows balance between compression ratio and speed. The probabilistic model is based on the finite context model, which estimates the probability of the next symbol of the information source to select the probability distribution. It's with the compressor splits the file into two streams, headers and the sequence itself, uses a single finite context model to encode the headers and uses competing finite context model to encode the biological sequence. On the other hand, the context mixing algorithm compressor is divided into predictor and arithmetic coder and work just like prediction by partial matching. Different from prediction by partial matching, this algorithm uses many models instead of one. In this slide, I'll explain how the Elfastekuc work. First, the Elfastekuc file is split into 4 streams: the read identifier, the quality score, and the optional plus sign stream, and lastly, the read sequence stream. The read identifier then will be tokenized into different fields, as well as the optional stream if existed. After that, the read identifier fields will be input to the context mixing algorithm compressor, and the quality will be sent to the context mixing algorithm as well. And the read sequence will be sent to the finite context model compressor. The final step is to tar all 3 files into a single file. And this step will not introduce any compression gain, just to make them in a single file. The decompression is to reverse the process. First, the tar file will be untar into 3 or 4 files. Then each compressed file will be input to the corresponding decompressor. The read identifier field will be joined into one file. And lastly, all 4 streams will be merged to regenerate the original Elfastekuc file. Our comparison reveals the following. First, besides Elfastekuc our tool, only 3 other tools were able to handle all data included in our datasets: Elfastekuc and the 2 general purposes compressor, gzip and bzip2. So among the 7 specialized Elfastekuc file compressor, we only have 2 reliable tools, Elfastekuc and Elfastekuc. Spring, Web, and FQZ comp were not able to handle the color space encoding that were generated by the solid technology. And Web Squeeze 1 and FQC comp also were not able to handle some of the dataset when the read length vary from record to another. In addition to long reads existed in the third generation sequencing technology. In 8 out of 15, our tool obtained the best compression ratio. In 2 cases, Elfastekuc share the first place with Elfaqc. Elfaqc has the best compression ratio in 4 cases, 2 which were shared with our tool. Spring has the best compression ratio in 2 cases, and FQZ comp obtained the best compression ratio in 3 cases. In terms of compression speed, TSRCC, Spring, Web, and FQC comp all show an astounding performance. And since we only have 2 reliable tools, Elfastekuc and Elfaqc, we compare them against each other in terms of speed. So when comparing Elfastekuc to Elfaqc, in 14 out of 15 Elfastekuc, our tools finish sooner than Elfaqc. The same is for the decompression speed. TSRCC, Spring, Web, and FQZ comp all finished way earlier than other. All these tools have high memory consumption that can reach to be linear to the input file like Spring. And when comparing Elfastekuc to Elfaqc, again, 14 out of 15, our tool performed better than Elfaqc in terms of decompression speed. Our tool memory consumption is very efficient because both compressors we use are using maximum of 2 GB. And since they run in parallel, they add to 4 GB for all datasets. And what makes Elfastekuc is the best is its higher compression ratio on most of the data. And it's compatible with all major sequencing platforms and its memory usage. We reached the end of our presentation today. Thank you. If you have any question, just let me know.
Thank you so much, Dr. Sultan, for the very, very informative talk. I really enjoyed it.
Thank you, Dr. Yusuf.
Yeah,
Thank you, Dr. Yusuf.
Nice. I really congratulate you again on completing your PhD. This is a very nice work, to be honest.
Thanks a lot, Doctor.
You're welcome. So now we will open the questions. If anyone has any question, please go ahead. Okay, I'll have a question about the sequencing platforms.
Yeah.
Dr. Sultan, to what extent do you think your work is applicable to any other field? Is it only mainly for sequencing platform, for example, the DNA, or could it be something applied to other fields, maybe medical or any other fields? What do you think of that?
Yes, so mostly our work is based on Huffman Tree, which is like part of data compression tools that existed already. And we have like a current work that we may apply it for the EGG signal. And it might be also applicable for any other medical images. But we need to first to understand the file that is generated by those platforms.
Okay, that's very good. Thank you so much, Dr. Sultan.
You're welcome.
Any other questions?
Yes, Assalamu alaikum. It's a nice presentation. I really enjoyed it.
Thank you, Dr.
So I have one question. So when you approach multiple non-greedy Huffman tree, you mentioned that you choose like you have tried multiple P. So you mentioned that there is like the best is between 1 and 3 MP. So I'd like to see like if I have a data and I need to apply it to, let's say, a file. And do I need does the program or the software need to search, or just like pick any number between 1 and 3 MB?
So actually, this is a future work. So for now, like I'm only partitioning the file into n equally partition, but in the future I will make it like smarter to choose like the best partition. Like so, I may have like 10 partition with like, and they vary in size. So the first one will be 1 megabyte, the second one will be 1.5, and so on.
I see. So you mentioned that it was decreasing when you reached some limit. The performance was decreasing.
Yeah. Actually, that is because of the file metadata. Okay. Because we need to encode the metadata in order to decompress the file. But as you see in the future work, I mentioned something about the metadata footprint. I need to reduce it, and I think this will help us or will increase the P partition before the degrading.
Okay, that's good. Yeah, so this is only the question that I have.
Yeah, thank you. Thank you for the question. Thank you again.
Thanks, Dr. Said, for your question. Do we have any other questions, please? Any other questions?
Dr. Sultan.
Yep.
Assalamu alaikum. Yeah, just one. Yeah, first of all, I would like to congratulate you on your achievement. We are in the college very proud and happy for your PhD achievement. And
thank you so much.
Yeah, we are so happy to inshallah to meet you in the college and to see inshallah your performance and action inshallah in the future, and to help us to continue inshallah our good performance in the research and the academia.
Thank you so much.
Yeah, and it's a naive question. Like, do you think your approach or algorithms that you have applied in the data compressions outperformed? I mean, better than the other approach, or what do you think, and why?
Yeah. So as you see in the presentation, like in the Elfastekuc file compression, I compared my work against the state of the art. And as you can see, in most of the cases, we outperform them in terms of compression. And we work, and this is our metrics that we work on, is to improve the compression ratio, and the memory usage as well, not the speed. So we beat them in terms of compression ratio. In the FASTA file, we only compare against the tools that are based on Huffman Tree, and we still have some future work. And as you can see, we developed 3 tools, and each one is better than the previous one, and we still like in the progress. So we are not in FASTA. We are not too far from the best compression tool existed for the FASTA. We're almost like 1% away, but we have like a better memory usage and better speed. So we're still on the track, and we will get it soon, inshallah. I hope this answers your question, Dr.
Muhammad. So I have a question to follow up with Dr. Muhammad's question. So I'm wondering, did you file any patents for these? Like, because you have supporting papers that you can just support your patent application. So did you file any?
I don't. No, I didn't.
Okay.
I didn't think about it this way, actually.
Yeah, so I think you can file a patent to this.
That will be great. That will be great. That will be great. Thank you. Thank you so much for mentioning that.
Yeah, so you have supporting like papers. I think no one will use the paper itself, but the product, someone may use it. So you may need to file it, and you have the papers to support the patent. So they have process, but you need to think about it.
Okay, yeah, sure, we'll do.
Okay, thanks.
Thanks a lot, Dr. Zaif.
Thank you so much, all. Do we still have any other questions? It doesn't mean we need to have another PhD defense, Dr. Sultan, but it's really interesting and everyone is happy.
Thank you so much.
So
I had enough.
All right, I think that's all for tonight. We really thank you again, Dr. Sultan, for the interesting presentation. Thank you everyone for coming and for your nice questions. Hope you really have a good night. Thank you all, and thank you, Dr. Sultan.
All right, thank you all. Thanks.
شكرا دكتور سلطان، الله يعطيك العافية ويوفقك إن شاء الله. شكرا لك.
ألف شكر دكتور محمد، يعطيك العافية.
الله يوفقك إن شاء الله. مع السلامة.
الله يحفظك.
موفق دكتور سلطان، موفق إن شاء الله. يعطيك العافية.
شكرا، يعطيك العافية دكتور سعيد.
يعطيك العافية دكتور سلطان، الله يبارك لك إن شاء الله.
الله يجزاك خير ولا يهينك دكتور مسفر. تسلم.
ثانك يو دكتور، والله يوفقك وإن شاء الله من أفضل دكتور. الله يحفظك.
تسلم دكتور تركي.
بالتوفيق دكتور سلطان، الله يبارك لك ان شاء الله. نشوفك ان شاء الله.
الله يجزاك خير دكتور مانع ولا يهينك.
Thank you, Dr. Sultan. See you inshallah in the college very soon. Thank you so much.
ان شاء الله دكتور اسد الله، ان شاء الله.
في امان الله دكتور سلطان، ما شاء الله.
في امان الكريم. شكرا دكتور علي، يعطيك العافيه. تسلم لي على راسي يا حبيبي.
شكرا يا دكتور سلطان، الله يعطيك العافية.
ألف شكر. تسلم دكتور محمد، يا مرحبا فيك والله.
الله يحفظك.
الله يستر عليك.
وفقك الله يا دكتور سلطان، شاكر ومقدر لك إعطائنا هذه الفرصة والمعلومات الرائعة، والله يوفقك ويسعدك إن شاء الله.
تسلم يا دكتور، الله يعطيك العافية ولا يهينك.
الله يحفظك إن شاء الله، بالتوفيق لك يا غالي. الله يحفظك إن شاء الله.
تسلم لي، الله يحفظك ولا يهينك. يا مرحبتين.